Lecture 24, Reliability, RAID. So, failure is always an option, at least if you listen to Adam. And the previous topic discussed the idea that we would want to use transactions in case there's a failure to ensure that system data is always in a consistent state. Right? Whatever we do, right, there's always a possibility that there is a crash in the middle of it for some reason, and although that's not nice and it's not something that you want, it's not necessarily within your control either. And so based on that, we said, all right, we have a plan. We will have transactions, and transactions involve taking detailed notes about what we plan to do. And based on that, we will be able to proceed, and we will be able to recover if something goes wrong. Right? That way we'd always at least get the data to a consistent state. The problem then, of course, is not solved for every kind of possible failure, because there does exist the distinct possibility that hard drives die. And that's in fact the note that we closed that topic on by saying, well, listen, you take backups, right? Because hard drives die, well, they do, right? So what do we do to account for the fact that hard drives die? Well, what I asked, or maybe I should phrase it, what Senator Amidala asked, was based around the idea of backups. Okay. Backups help, but they're not the only way. Backups could easily be out of date, right? If you have daily backups, potentially you could lose up to one full day's work, because whatever's happened between the time of the failure and the time of the last backup is potentially lost, right? If you have hourly backups, that reduces the pain to a certain extent. You can lose up to an hour's worth of work. That's probably less painful, but I guess it really depends on what the work was, doesn't it? So it's a decision that you're going to have to take, right? Potentially, actually, if the disk dies, right, you need to replace it. Maybe that's not instant, right? Maybe you have to go out to the store and get a new disk. I'm guessing you probably don't keep too many spare drives around in your home in case something goes wrong, right? So probably you need to get a replacement part, and then it takes time to copy the data from the backup storage location to the new one and get the system going again. So okay. Finally, there is also a saying that says you only really have backups if you've tested that you can restore from those backups successfully, right? That's not always something that you test, right? You tell, okay, we've successfully copied the data from one place to another, and does that work? Yes, okay, good. But you also have to be able to restore from those backups. If that doesn't work, you're going to find out very quickly in the emergency situation why this is a big problem. Right? It's not enough to have it. It's like you've tested. I don't know it's like having life jackets on your boat. You can verify that you have them, but if they're supposed to inflate or whatever, if you've never tried inflating one, how do you know that they actually work? Okay. So here's the thing, right? Hard drives die. Here's a dead one, okay, this one isn't quite the dead one that I bring into class for people to poke at, and if you attended the topic where we talked about how magnetic hard drives work, then you might have actually held a dead hard drive of mine in your hands, this is unpleasant, but it happens. So as it stands, the untimely death of a hard drive potentially means a loss of data. This would be a decrease in reliability, although we're going to talk about that subject in a bit. And until that situation is addressed, the system is down, it's unavailable, which would be a loss of availability. So, okay, we're going to talk about the subjects of reliability and availability in the next topic, but both of those things are desirable properties, and so not having them feels bad. Maybe though it's not actually that dire, maybe we just have sort of reduced performance. But okay, what if I told you that there exists a solution where you not only get higher reliability, higher availability, but maybe also better performance? Well, I mean, Thor thinks that that's not possible. Um, but, well, I'm going to say it is. And, I mean, it's not magic, right? It does cost money. It's not wishful thinking, like, this is achievable, but it does cost money, but maybe not as much as you might think, right? There's lots of things we can do with even a relatively modest budget that would increase both reliability, availability, and come with free performance, maybe. But if all your hard drives die at once, right, there will be data loss. Similarly, if your data center catches fire and burns to the ground, it decreases availability. But for common scenarios, there's a lot we can do that will reduce the likelihood of a problem. And the solution is called absolutely not. More memes where I can't actually say the full thing out loud. Don't want to make YouTube mad. Okay, no. The solution is called RAID, but it has nothing to do with exploiting people's gambling addictions. RAID is an acronym for Redundant Array of Independent Disks. And previously, when this was introduced, it was first Redundant Array of Inexpensive Disks. Yeah, whether disks are expensive or not is a question of budget and what you want, but yeah, now it's Redundant Array of Independent Disks. The idea, in short, is to have multiple independent disks that work together but appear to the user as if they are one drive or one volume. This RAID array may be managed in either hardware or software. It doesn't actually matter for our discussion today. We're just here to learn about like what is RAID and how does it work, and whether it's managed in hardware or software is not particularly important for this discussion. So the idea behind it effectively is, if we combine more than one relatively inexpensive disk, we get higher reliability than if we spent more money on higher quality drives. Hard drives have become less expensive in general, so the independent part has taken over the letter I. But okay, how much redundancy do we actually need? Right? This is a design goal of the system. And you choose what makes the most sense for your system. As I've told you, I lost the hard drive in 2014, but I wasn't upset about it because it contained my Steam game library, and it was easy to just download and reinstall those games again, even if, yes, like everybody else, I haven't played most of the games in my Steam library. Not having redundancy there is okay because, to some extent, Valve Corporation is the source of my backups, and losing that data was lightly inconvenient, but not a tragedy, right? That's not a big deal. The files that were on there were not family photos or something that would otherwise not be possible to find again. So okay, it's it is inconvenient but not a tragedy. On the other hand, if you have a database that's backing up your web application, like for your software as a service company, downtime is going to be a problem. Right? I mean, downtime in this sense means like we lose money, which obviously is undesirable, so we would like to avoid that. Right? There's lots of different levels of redundancy that make sense depending on your use case. So for any device, whether it's a hard drive or not, I mean, we can also talk about it for other devices as well. We can talk about a figure called the mean time to failure. And the mean time to failure is always an estimate. If this is the first time that ABC Corporation has produced this particular device, they don't know really how long it's going to last. They may be able to compare it to the previous year's version and maybe some internal tests to try to guess about how long it's going to last. But it's hard to know really if the device is going to last 10 years until actually 10 years have passed, because until then it's just guessing, it's just an estimate, it's just based on, well, we think, and our models show kind of stuff. But on that subject, it's hard to know actually if the usage patterns that are used in the model are realistic, right? Graphics card manufacturers may assume that you want to use your RTX 3080 to play Cyberpunk 2077 and base the lifetime estimates on you play this game X hours per day on average. But if you overclock your GPU and use it to mine cryptocurrency, please don't do this, but if someone did, then its lifetime will be shorter than expected, because using it at maxed out, overclocked, full capacity, 24 hours a day will most likely cause a failure sooner than expected. I mean, in this case, right, it's heat. Heat is the enemy, and it will damage the components over time. So we don't want that, and so appropriate cooling and what have you can help alleviate this. But whatever facts, figures have gone into the idea of managing the mean time to failure, it's based on an estimate of how they think it's going to be used, and that may be wrong. Okay, so how bad is the problem? Well, let's say that you bought a disk that says its mean time to failure is 100,000 hours, which is a nice round number that corresponds to approximately 11.4 years. Okay, you might think that's perfectly fine. Even if it lives only half its expected lifetime, that's more than 5 years, and you say to yourself, I'll replace it before then. Whether you will or not depends, but realistically, 5-6 years is well within its expected lifetime, and maybe you can push it to 7, but does that work? Well, here's the thing. If you're running a data center and you have 100 of these drives, in the meantime to failure is really 100,000 divided by 100, which is about 1,000 hours or 41.66 days. So, okay, you should actually expect that every month and a half or so, one of these dies. All right, here's the problem with this. The problem with this example is that it's not realistic. Because, I mean, do you have exactly 100 identical drives? Maybe not. But also, it makes it sound like deaths are evenly distributed, where, every 6 weeks, one drive dies. That's not what actually happens. It's much more likely, in fact, that everything is fine for a while, and then drives start dying in quick succession. So that's worse to a certain extent. So, as the saying goes, no free lunches. If we want to have improved reliability, there will be a cost associated with this. And the cost is in redundancy. However you want to approach it, if we want to prevent loss, we need to have more than one copy of the data, such that those different copies are stored on different physical storage media. And therefore, this costs more money in sort of one of two ways. Either we have to spend more money to get more disks, or if we have a fixed budget available, we're trading some of the total capacity for redundancy, right? Both scenarios are sort of easy to visualize. If you want to have redundancy for a 2 terabyte drive, you could buy a second 2 terabyte hard drive for redundancy, or if the math works out like this, use the same money to buy 2 1 terabyte hard drives, and that's just how you go about it, right? Either it costs more money to have that reliability, or using the same money, you don't have quite as much capacity available. Okay. Right, and so the first thing that we could think of immediately is this, okay, we have 2 identical drives, or at least 2 drives of the same size, and that's our approach. And if we do that, then the way to get data redundancy is mirroring. Right, this means that the data on each drive is, as close as possible, exactly the same. Well, if one disk dies, then the data is on the other one, and the data is not lost. Right, so that's good. Of course, having lost one of the disks, it's important to replace the dead one so that the reliability is restored. Otherwise, we're in a more vulnerable position to data loss, having lost a drive, such that we have to rely on just the one remaining drive to keep it going. So how fast do we have to replace the second disk? Okay, I mean, you want to do it as fast as possible, but what does the math say about how quickly? Well, again, if the mean time to failure exists, then there exists sort of an equivalent concept called the mean time to repair. And the mean time to repair is like how long would it take to get a new disk and put it in the hard drive, in the enclosure? Like how long would that take? And 10 hours seems kind of reasonable, right? You have to be notified that the drive died. Maybe that's in the middle of the night. Maybe you can't just pop by the computer store because it's 3:15 in the morning. And that's okay, right? You can wait for them to open at 9 o'clock the next day. And then go and install it. All right, that takes a few hours, but it's within our sort of mean time to recover. Okay, and so given a figure like that, the mean time to data loss is calculated as 100,000 squared divided by 2 times 10 equals 500 times 10 to the power of 6 hours, which is on the order of 57,000 years, right? Is that a realistic estimate? So what we're saying effectively is how long will it take before there's a situation where disk 1 dies but cannot be replaced in time before disk 2 dies, right? Without loss of generality, right? It could be disk 2 dies and needs to be replaced before disk 1 dies. Assuming we attend to the problem quickly, you can imagine that actually this scenario is pretty rare, right? As long as we jump on it and get there quickly, that reduces the mean time to repair and accordingly increases the potential lifetime of the system. Is that actually realistic, though? You see, part of the problem here is that we are assuming that disk failures are independent. Are they? I mean, independence is a statistical concept that's somewhat complicated to talk about, but our expectation is not that disks will survive 57,000 years. That seems unrealistic. I'd be amazed if they lived through 50 years, never mind 50,000. And it's just that hypothetically, if a disk dies and we replace it fast enough and maintain this watch forever, then we expect the average time before we lose data is 57,000 years. But that's not actually realistic, right? Because, as I said, these events are not independent. We treat 100,000 hours mean time to failure as, okay, this is the realistic estimate for each drive, and each drive is independent. But that's not true, right? Leaving aside things like external forces, data center catches fire, which causes 2 hard drive failures back to back because the hard drives are located in the same physical place. It's entirely possible that if we bought 2 disks from the same manufacturer from the same manufacturing run, that both these disks will live about the same amount of time, right? And it's not it's not independent because they are from the same manufacturing run. And it makes it more likely that they die closer together and not randomly distributed independently. And incidentally, one of the common causes of failure of recovering data is that if we do throw a new disk into the system and we have to copy a lot of data from the old disk, that's a very heavy load. And if the surviving disk is already in poor health for whatever reason, it's already sort of feeling kind of fragile, it's possible that this actually pushes it over the edge and causes it to die. Oops. Okay, so the mirroring approach means that there is additional cost to every write. Every write needs to be done 2 times, 1 time on each disk. Usually that can be done in parallel, so there isn't actually a large amount of cost to it in terms of time, but it is still effort. But more concerning is when there are 2 writes to 2 different drives. We do have to face the problem of what happens if one of the writes succeeds and the other one fails for some reason. It's a good question, but we'll save that for the moment because actually there's more arrangements possible than just mirroring. So let's talk about some of the options, or as I call it, level please. So RAID is described as having numerous different levels. And each level represents a different configuration of the available hard drives that are employed in the system. And each of the levels has a different configuration, and I don't want you to think of it as higher number is always better. Right? Different levels are appropriate for different use cases, and you should choose the one that makes the most sense for you. And there's no reason to think necessarily that this number is strictly increasing in terms of usefulness or in terms of redundancy or something like that. You choose the right level based on your needs, but also your budget. And there are 7 basic levels that have sort of broad acceptance in industry, and they're RAID 0 through 6, but there are also a couple of combinations of those. In some of the research literature and some companies' publications, there are like different levels or different numbers, but just for the sake of time, we will restrict our discussion to what I'll call the commonly accepted ones, and these are the things that you would find in a textbook, and they are, like I say, broadly, they mean the same thing to everyone when you talk about them. Even amongst the levels that exist, not all of them are commonly used, as we'll see, but let's go through them and we'll talk about them first. So option 1 is no thanks. Right? It wouldn't be right to fail to include the do nothing option, which is to say no RAID configuration at all. And I used to tell students when I was a work term report marker that sometimes you should actually put in your analysis like the do nothing option. Even if the do nothing option is bad, if we do this like we lose money or something, that's fine. Just like make it clear to the reader why we have to do something, like why the problem needs solving. And so, yeah, the do nothing option warrants at least a mention. And the do nothing option is also sometimes called JBOD, just a bunch of drives. Right? There's no actual RAID configuration. You just have the disks. They're not configured in a RAID array. You treat them as individual disks. No redundancy, no reliability increase, but it's entirely manual how you want to handle this. And that's not entirely insane, right? You could say to some extent that using an external hard drive for backups is like this. You connect the drive, you copy the data, you're managing it yourself. You copy the important files so they're on the backup drive, so you have another copy of them, and it guards against data loss, but it's not part of a managed integrated system. That's okay, right? And in the scenario where I had the computer that had the hard drive die, right, I had 2 drives in the system. I had like the main system drive that had Windows and the applications, most of them anyway, and then I had the second drive that like mostly had the games on it, right? Those were 2 independent hard drives. Whether they were inexpensive or not, I don't remember at this point because it's been a while. But they were not managed in any sort of RAID array, so we would call it this just a bunch of disks kind of organization. Okay, first option is called RAID 0. And RAID 0 is, what redundancy? And this is disk striping. So it splits the data and files across multiple disks, so that disk 1 has block 0, disk 2 has block 1, disk 3, and so on, depending on how many disks you have. In the textbook, the blocks are referred to here as strips, and that's distributed. So an individual file, in this case, could easily be spread across all 4 disks that appear in this system. Okay, this is weird, right? We talked about I want redundancy, and I want more reliability and what have you, and now I'm saying actually no thanks, forget that, I want to go fast. The major advantage of RAID 0 is actually that it is fast, right? A write can be done in parallel, so writing a file that has many blocks to a RAID 0 array of n disks can be done n blocks at a time, which is potentially a significant savings, so it increases the parallelism by a factor of n. And similarly, reading a file from disk can also be sped up by a factor of n, depending on what you want to read. Right? If you're trying to just read the whole file into memory, then absolutely, that is effective. If you're trying to jump around, maybe it's not n times faster, but it's okay. So here's the thing, right? There's no redundancy in the system. In fact, it's worse, right? It's faster to do reads and writes, but if one drive dies, then all of your files are ruined, right? Like all your data potentially is lost. That kind of sounds bad, right? The topic we're supposed to consider here is reliability, and this sounds like the opposite of what we want. I mean, who doesn't like to live dangerously, right? I mean, I don't, but I don't recommend this, but you could. There are actually scenarios, though, in which you would be fine with the risks of RAID 0. If you have a transit app that gives you the bus and subway and train schedules, instead of retrieving them from the database on every request, you can keep them in a cache. And if memory is big enough, great, keep them in memory. But if they need to be on disk, you could have a RAID array of a couple smaller disks, so you get better speed for reading and writing stuff from the cache. Right? We can certainly live with the fact that any disk's untimely death takes the whole thing down, because the cache is just a more easily accessible copy of the original data, and it's trivial to regenerate the stuff in the cache at any time. So sometimes we're okay with this. Sometimes the thing that we need is speed, and we don't really mind. Another reason why we might want to use RAID 0 configuration is because we want to combine it with another option. And we'll talk about that a little bit later on, after we finished covering sort of the levels that we've set out for ourselves. Then there is RAID 1, and RAID 1 is mirroring. And when we have mirroring here, right, we have sort of identical copies of our data, right? The data that appears on each disk is replicated exactly to another disk. We have to have an even number of disks to make this work, of course. And this is actually very easy to explain, very easy to understand, right? Every time we write the data, there's 2 copies of it. And yeah, that makes sure that we have redundancy, reliability, and it can actually improve our read speed at least a little bit, right? Half the disks are mirrors of the other half. Read speed is improved because any piece of data could be found on one of 2 disks, so we can get the data from the less busy drive. If it's a larger request, we can read from both disks in parallel and get our data a little bit faster. If we have many more reads than writes in our application, that's maybe a significant performance increase alongside the improvement in reliability that we would expect. Replication, as I say, is fine. In terms of write speed, right? It's no worse than writing directly to one disk because there's no write penalty. If one of the disks is busier than the other, though, you might end up effectively being limited by whichever of the 2 is a little bit slower. You could choose to do it asynchronously, where you schedule it and we write it to one disk, and then asynchronously we carry out the replication to the other disk. That does introduce the headache of what happens if the replication fails, or 2 different in-progress transactions do not complete. There are tools to deal with those sort of scenarios, transactions, recovery, or even NVRAM. NVRAM stands for non-volatile random access memory, which will have some amount of battery power, so it can complete operations even if system power is cut, so that you can ensure that an operation that's requested is actually carried out. There's options, right? It's not hopeless in this regard. And then there is RAID level 2. And I got to tell you that RAID level 2 is, actually, before we go on, to finish up about RAID 1, should one of the disks be unavailable, right? We can just get whatever data we need from the surviving disk. Okay, that's sensible. Our read speed may be reduced in that case, but it's no worse than having just one hard drive. If we have 2 disks, it makes sense that our usable capacity is half of the purchased capacity because each disk is an exact copy of the other. If we have 4 disks, 2 disks are a copy of the other 2. 8 disks, as shown on screen, means 4 and 4. It's excellent for reliability, but on the other hand, the scenario that we want to guard against usually is like the failure of one drive, right? And does it seem a little bit of a problem that like we're using 4 drives now as backups here? Is that more overhead than we're willing to tolerate? What if we didn't need quite as many disks? If we just wanted to guard against failure of 1 disk? Okay, so RAID 2 looks a lot like how memory does error correction in ECC RAM, ECC error correcting code RAM, and it uses parity bits in memory to detect if there is an error. And I'm hoping that you remember something about parity bits and Hamming codes and such from an earlier course, because that's the sort of scenario that we are thinking about. This is the approach that we use. So if you want to detect single bit errors, right, each byte has a parity bit that is 0 if there's an even number of 1s in that byte, and the parity bit is 1 if there is an odd number of bits that are 1 in that byte. In the event of data corruption of some sort, right, we can detect the error, but it is a little bit hard to know which bit is flipped in this sort of 1-bit scheme. If we have a 2 or more bit parity scheme, we can correct single bit errors and detect 2-bit errors. And the trend really continues, right? More parity bits equals more ability to detect and possibly correct errors. There is accordingly more overhead, right? Having 1 extra bit for every byte is one out of every 8, so 12.5% overhead. Having 2 bits is 25%, and you can see it's starting to get a little bit expensive beyond a certain point. ECC can also be used in disk arrays, and one such example is if you have the first bit of each byte is stored on disk 1 and the second bit on disk 2, such that the 8th bit of each byte is stored on disk 8, you can have yet another disk that stores the parity bits. So you have like bitwise distribution of your data. And yeah, in the event of the loss of one of the disks for each byte, you have 7 of the 8 bits, and you can work out from the parity bit whether the missing bit should be 0 or 1. You don't actually need 9 drives for this, although it does make it very easy in an example, right? You would just use modulo to make it work. If you had 4 drives, okay, bits 0 and 4 are on this drive. That's fairly easy, I think, to imagine, right? Based on this scheme, a read-or-write will necessarily engage all of the disks in the array, so that it can read data and write data quickly, but it's also extremely painful to split up every single read and write to the bit level. It might work better for large files because we could read multiple blocks at once, but for small files it requires reading 8 blocks of data where 1 would normally do. So random access performance is poor with RAID 2. It does have lower overhead than RAID 1 in the sense that you don't have 50% of the disks given over to replication, but it's still pretty high overhead. If you have 4 disks of original data, you might need 3 parity disks for it, and it's very hard to come up with use cases for RAID 2. It maybe makes sense in a world where a lot of disk errors occur and data elements are frequently corrupted, but existing hard drives are sufficiently reliable that there's kind of no point to this. So RAID 2 is not a commonly used scheme. Then there is RAID 3, and it looks a lot like RAID 2, but instead of having each bit spread across different disks, a byte is spread across, each byte is spread across the disks, and parity is slightly different. The parity bit is computed for the set of bits at the same position on all of the data disks. And so there's an example for this of how to calculate the parity. If we have hard drives D0 through D4, and D4, the last one, is the parity disk as we see here. Right, the parity bit for bit I is D4. For bit I is calculated as D3 XOR D2 XOR D1 XOR D0. Where if drive 1 has died, you can recover the data by calculating D4 XOR D3 XOR D2 XOR D1. Like RAID 2, every read or write needs to be performed synchronously across all of the disks, and this can help to some extent with speed because the data is being accessed across multiple devices simultaneously. But we may end up with a lot of extra reads if we are trying to read a fairly small file. One advantage of RAID 3 over RAID 2 is that you only ever need one extra disk for the parity information, as compared to 3 if you had 4 disks in RAID 2, and 4 parity disks if you had RAID 1 configuration, right? There's a lot less overhead because, having only one disk for redundancy is a lot better. But there is a lot of computational overhead of doing the parity math, even though this is relatively small in comparison to the cost of disk reads and writes, although this is relatively small in comparison to the disk times and can be offloaded to hardware. Another thing that's nice in the RAID 3 scheme is that if a disk fails, data is available, but it's somewhat slower, right? Any missing data can be compensated for by calculation of what it should be using the parity information. Writes will need some additional information, some bookkeeping, so that when the system is restored to full functionality, everything is where it should be. However, it is nice to know that the system can continue executing, even if it's in a reduced capacity, until the problem is solved, as opposed to just being offline and unable to continue. Okay, again, RAID 3, not particularly commonly used though. And then there is RAID 4. And RAID 4 looks like both RAID 2 and RAID 3 to a certain degree. And it is, instead of having bit or byte level parity, we have block level parity. It is an acknowledgement that the hard drive is fundamentally a block-based device, and we've spent lots of time talking about like how it operates on one block at a time. And it only seems sensible that the parity scheme should take this into account as well, right? So there is block level striping in the system, just as there is in RAID 0, and parity blocks are stored on a dedicated parity disk. As with other schemes using parity, data that's lost due to the failure of a disk can be restored by doing calculations using the data on the other disks. But what's nice here is that unlike RAID 2 or 3, each disk can independently be accessing a different block at the same time, because it's not that every byte of a file is distributed on a modulo system across different disks. It's now you want to read this block N of a given file. Well, you can figure out it's stored on disk 2, and you just go there and get what you need. So that's kind of nice. There is a little bit of a penalty for doing any update. If the update is small because a whole new block is written, writing the parity block for it is straightforward. But if we're not writing a full block, then when we actually make the modification, we have to read the block after the write is complete to recompute the parity information for that block, making the modifications here a total of 2 reads and 2 writes to actually accomplish the goal. One potential downside in this case is that the disk containing the parity information is sort of a bottleneck device of the system. It is going to be modified a lot. This drive may actually be worn out sooner than the others in the system, which doesn't sound terrible. I mean, hard drives have fairly long lifetimes, but it is hypothetically possible. And it's more of an issue for solid state drives, because solid state drives have the possibility of having their writes exhausted. So it is a little bit concerning. But actually RAID 4 is not that common, because a slightly better version of it exists called RAID 5. And RAID 5 is just like RAID 4, except instead of having one disk that is dedicated solely to the parity information is distributed across all disks. That is, each disk has some data of its own, but also some parity information of other disks. And parity information is typically stored in a round-robin fashion, but a parity block can't be stored on the same disk where the original information is, because that would mean a loss of that disk would also result in an unrecoverable loss of data. So maybe it's not quite as simple as just this modulo that, but that is fine. RAID 5 is, in my experience anyway, and also according to one of the textbooks, the most common parity RAID system. It provides a lot of what we've been looking for: reliability to avoid data loss if any one drive should die, without doubling the number of drives needed. And if we need multiple blocks from a file, potentially we can get at least a few of them in parallel, depending on how the data from the blocks is stored. And writing something to disk is not as complicated, right? We just write it to disk and update the parity information, and then we go on. And then there is RAID 6. And RAID 6 is like RAID 5, but it has extra information that allows the system to survive more disk failures. And rather than parity or some error correcting codes, right, we have just more redundancy, allowing the system to survive potentially 2 disk failures. And that's a design decision, right? Like, what are we comfortable with? Do we need to survive just one drive failing? If that's the case, then RAID 5 is probably adequate. If we would like a little extra reassurance that the data isn't going anywhere, then maybe RAID 6 is the better choice. With that said, in a RAID 6 system, there is a substantial write penalty because every write requires updating 2 parity blocks. Tests show that RAID 6 has read performance at about the same speed as RAID 5, but writes are about 30% slower. So that is a non-trivial penalty, right? 30% slower write speed is actually noticeable, but how often do you do writes as compared to reads? And also, like, how much performance are you willing to trade for redundancy? And then, of course, there is the idea of combining levels. And when you combine levels, you end up with something like, they call them 0, 1, 10, 50, something like that. But what you should actually think about them is as something like 1 plus 0 rather than 10, because what we're doing is we're combining a RAID 1 and a RAID 0 at 2 different levels. And so here's like an example of RAID 0 plus 1 and RAID 1 plus 0 to sort of show you the difference between them. And in each of these examples, the little cylinder with an X on it represents a disk that has ascended to Valhalla. But RAID 0 plus 1 is we have 2 RAID 0 arrays, and on top of that we build in mirroring, so we have a RAID 1 of the combined disks. If we have 4 disks in total, we have a RAID 0 formed of disks 1 and 2, another RAID 0 formed of disks 3 and 4, and then we build a RAID 1 array of the 1 plus 2 and the 3 plus 4 disks. Or in this example, right, we have a RAID 0 of 4 disks, and then a mirror to another RAID 0 of 4 disks. On the other hand, right, you can go the other way, and with the RAID 1 plus 0, right, we have mirroring of each individual disk, and then we build a RAID 0 array of each of those, combining each of those into one big disk. Okay, right. In principle, you can combine any strategy any number of times. Every time a group of disks is combined using a particular RAID level, you can treat it as a single disk, as input to the next level. And it does allow you effectively an arbitrary degree of RAID redundancy and what have you, according to your wishes, according to your needs. So given all of this, there's the question about how do you choose the right level for your system? And there's no obvious answer because there are lots of situations where data loss is more or less important depending on your application. So here's some questions to sort of help you to decide. Question 1, how critical is it that data is not lost? If the data that you need is not critical in any way and it would be perfectly fine, you could just restore it from some other source. If the data was lost, then you probably don't care that much about redundancy, right? Maybe you only care about speed in that regard. Maybe that's a perfectly sensible choice for your situation. On the other hand, if this is critical data, it's the database that manages your taxes or something, right? That's important, and we don't want to lose that data. I mean, you could ask taxpayers to submit stuff again, but they're going to be really mad. So maybe don't do that. Maybe this is critical data, and we really can't afford to lose it. That's possible, right? And so in that scenario, we would choose something that has more redundancy. We would choose something that has sort of more more parity information to make sure that we really do not lose any of the data that we have. The next thing is, what is the budget? Because increased reliability typically costs more money, and that's okay, right? The things that we want usually do cost money, but how much budget do we have? Because if this is supposed to be truly critical information and we have as much budget as we need, then go nuts, right? Put lots of redundancy in the system, but if our budget is more constrained, then maybe we choose something that doesn't have quite as much reliability but works for our budget. The next thing is, how important is performance? Is that actually critical? Is that something we really need? Are we trying really hard to get our data out as quickly as possible? If that's the case, then maybe something like RAID 0+1 kind of approach might be beneficial, because it helps us to get data quickly while still giving us some amount of redundancy. But maybe it's just, we need faster reads because reads are much more common than writes, in which case RAID 1 is fine. And when we talked about RAID 6, we also sort of covered the idea that, it's got more redundancy, but write performance is a lot worse as compared to RAID 5. So again, which of those are you comfortable with? Next question is, do we need to be able to carry on at a reduced capacity in the event that a disk dies? If the answer to this is yes, then choosing one of those systems in which we have parity may be beneficial, because we can just calculate, we can compensate for any missing data. But it also works for RAID 1 in that, when we're down to one drive, we can just pull the data from that drive, and it's okay if its partner is not there. And we didn't really touch on rebuild in the topic, but it can actually matter. So if you have like a RAID 5 array and one of the drives dies, right, you swap it out, you replace it, and then there's the rebuild time where the data is restored to that drive that has been replaced. This potentially takes a non-trivial amount of time. And during that time, right, your system is very busy trying to copy all the data from the parity blocks and calculate it and trying to restore all the data that should be on that drive. How long that takes is a question of how much data did we need to put on that drive, and how powerful your system is. And so choosing something where it's relatively easier or harder to rebuild the data may have an impact on what is downtime when your system faces a problem. Okay, so I think at the end of the day, right, it's fair to say that there are no one-size-fits-all answers, right? There are different levels, and even though certain levels, particularly RAIDs 2, 3, and 4, and to a lesser extent RAID 0, are not very popular for usually obvious reasons, at least based on what we've talked about so far. Right, choosing between the RAID levels is a matter of your use case, your budget, and your goals, and it's okay if your solution to a particular problem looks a little bit different from somebody else's, because they have different objectives or they have different goals. So choose what makes sense, but also choose what you can afford. All right. So the discussion of RAID has been kind of an interesting introduction into the idea of reliability. And in our next topic, we are going to spend some more time talking about reliability in general, with hope of having a bit more formal discussion about what does it mean for systems to fail and what does it mean for them to carry on at reduced performance level.